Hello, the topic is TLC and it is the second video on that. So, when we talk about TLC, that is thin layer chromatography, it can be either carried out by adsorption principle if you are using the adsorbent like kieselguhr or alumina to prepare the thin layer of the chromatographic plate, then it is adsorption principle. And if we are using silica gel that holds water. So same like your cellulose paper in the paper chromatography. So when a thin layer chromatography is performed by using a thin layer prepared by substance like silica gel, it works by principle of partition principle. So when we are talking about thin layer chromatography, we are going to use different types of substances to prepare the thin layer depending upon the purpose of the process, that is chromatographic separation, which is going to be mainly dependent on the analyte to be separated from the mixture. So in the thin layer chromatography, we are going to have stationary phase, so which is coated onto glass, alumina, or plastic. And the stationary phase, as we can have silica gel, we can have aluminum oxide, cellulose, polyacrylamide, magnesium sulfate, and so on. Now, when it comes to the principle of TLC system, it is about separation of the analytes, and the separation is on account of uh, the different affinities of the stationary phase and mobile phase the analyte has. So, analyte is going to interact with the stationary phase depending upon the functional groups present on the analyte and that too on the stationary phase. For example, if we talk about silica gel, it is SiOH. So these hydroxyl groups are going to interact with the functional groups on the analyte. Of course, pre-treatment of silica gel also is done. Of course, it is going to be dependent on the purpose of the mixture to be separated. So selection of silica gel when we talk, we are taking into consideration SiOH groups which are going to interact. Of course, these OH groups also can be modified. Now, the affinities of the analyte towards the stationary phase and mobile phase are going to decide its separation. If it is more going to interact with the stationary phase, it will be retained more on the stationary phase and its movement along with the mobile phase will be less. So it will travel less distance. If the affinity of the analyte towards the mobile phase is more, it will move along with the mobile phase faster and move faster and will get ahead of all other analytes. The adsorption capacities of each component in a mixture for the same adsorbent are different, right? So we have to take into consideration the factors, that is the partitioning coefficients. The analyte is going to get distributed or partitioned between the stationary phase and mobile phase. So the concentration of the analyte in the stationary phase divided by concentration of the analyte in the mobile phase. This ratio gives you partition coefficient, which is denoted by letter K, and the formula goes as K is equal to Cs by Cm. The TLC is generally used for one of the three purposes, that is qualitative analysis to determine just the presence or absence of a specific analyte in a given sample. Second is quantitative analysis, where you are going to determine precisely and accurately the presence of the analyte and quantifying its amount that is present in the mixture. And the third purpose is preparative analysis, where purification is the aim. So, from the mixture, the analyte is to be isolated and purified. And this how you are going to have three different purposes for which TLC is going to work. On the same slide, we are seeing a formula that is RF, that is the distance traveled, the retention factor. So distance traveled by the analyte and the distance traveled by the solvent front are to be taken into consideration. So distance traveled by the solvent front, right, that is df divided by the distance traveled by the analyte is the retention factor denoted by Rf. So when we complete the process of TLC, we are going to take the TLC plate out, dry it, and measure the distances traveled by the solvent front and that of the analyte. And then we can have the ratio, and that will tell us about the RF factor of the particular analyte, as well as this RF distance, RF or the relative retention factor can be used to find out the nature of the molecule. Because when in a given TLC system, when we run a mixture of, say, sample A and B, it is going to give us a retention factor X for A and Y for B. But if we change the solvent system, then the RF values are going to be different. They may be M and N, they may be A and B, and so on. It will not exactly match with X and Y. So in a given solvent system, when we run a mixture of analytes, it will give us separation depending upon its interaction with that solvent system. And that's why the distance traveled by an analyte in a TLC system using one solvent system will give us RF1 for that analyte. But if we change the solvent system, the RF in the second solvent system is not going to match with the RF which is obtained by the first solvent system. So with change in solvent system, RF value is going to get changed. Now let's talk about the thin layer that we are going to prepare, the silica gel that we are going to use for preparation of the thin layer plate. So a slurry of a stationary phase is generally prepared in water. Sometimes people also use organic solvent like chloroform. So this slurry is made and is applied onto the glass or plastic or the enamel foil. Generally 20 centimeters square is the size of the plate, and at one end we start spreading the amount of the slurry. So you are going to pour the slurry on one end of the slide, and then you are going to spread it to the other end of it. So the slurry is going to move progressively to the other end of it. It needs to be done in a manner that the thickness of the slurry, that is the layer which is going to formed, it should be uniform, and thickness should not be more. So in order to get good separation, 0.25 millimeter thick uh, slurry would be better for analytical purposes. And when it is preparative separation, it may be up to 2 millimeters. So depending on the purpose of the TLC, we are to decide the thickness of the slurry layer. This stationary phase is to be used for adsorption chromatography. A binding agent also is added. So generally calcium sulfate is incorporated into the slurry that will help better adhesion of the adsorbent onto the plate. With the exception of thin layer exclusion chromatography, once the slurry is prepared, the plates are dried to leave the coating of the stationary phase. In case of adsorbents, drying is generally carried out in the oven at 100 to 120 degrees Celsius. Because of heating or baking of the plates, it is going to facilitate activation of the adsorbent, and then it is going to give us better separation. So when it is about preparation of a layer of the stationary phase slurry onto the slide, we can just go by bring it at one end and uniformly distributing it to the other end just by changing the angle of the slide that is going to have the particular thin layer formed on. It can also be done by spraying. So slurry is diluted, and with the help of sprayers, we are going to develop a uniform thin layer. So either by spraying or spreading, we are going to have a thin uniform layer. Modern methods they utilize the spreading devices for preparation of uniform thin layer on the glass plates. And commercial spreaders are of two types: moving spreader and moving plate type. So either the spreader moves in the first type, and in the second type, the plate moves. The spreader is standing still. And generally, the thickness of, as I said earlier, zero point 0.2 millimeter when it is for analysis purpose, and when it is for preparative purpose, you are going to have a thick slurry, and the thick slurry layer be prepared. So about zero point 0.2 to 2 millimeters is going to be the thickness of the thin layer that we are going to use. So, of course, the glass plate that we are going to use should be cleaned, and there should not be any residual of previous treatment. So, it should be dry, clean glass slide, which is previously cleaned with soap and water. And acetone wash also is given to remove if any fatty materials are there, and then it is dried in the oven. After preparing the slurry, the TLC plates can be prepared, and for which we can use the spraying type or the spreading type method. So pouring of the slurry, it is commonly done at the laboratory setup. The students can pour the slurry, or they can use the spreaders. So once this TLC plate is prepared, we can allow it to set and wait till it sets properly. So when it is about classical TLC plates that are prepared by pouring or by spreading methods, we have ready-made TLC plates available on the market which can be purchased and directly used. While handling, you have to take proper precautions, that is not to touch the surface of these uh, ready-made or the prepared chromatographic plates, because your finger impressions or the dust is going to interfere with the analytes in the mixture. So with proper handling, that is, gloves are to be put, you have to hold your TLC plate at its edges. Don't touch on the layer of the gel that you have sprayed it, or if it is a ready-made plate, then also you have to hold it at its edges and not in the center. You are not going to touch that. So once these TLC plates you are going to uh, prepare, or you are going to buy the commercially available ones, which are also called as polyamide layer sheets, which consist of polycaprolactam and are coated on both the sides of the solvent resistant polyester sheets. They are also available. So, a variety of ready to use TLC plates are there on the market. You have to choose the right one, and of course, cost effectivity is to be taken into consideration. Now, once your TLC plate is ready, you have to go for application of sample. Now, when we say about classical TLC, the thin layer has thickness of, as I said earlier, 250 microns and 10 to 20 micron particle size that is used. So it is going to permit analysis of 10 or less number of samples. When we are talking about application of sample onto the plate, very less amount, that is zero point 0.1 to 1000 microliter amount maximum, that is to be applied onto the surface of the PLC plate. Now this can be done using a simple capillary, glass capillary, which you are going to dip into the dilute solution of your analyte, and you are going to carefully touch the tip of the capillary onto the TLC plate and release a very small portion of the analyte onto it. It should not exceed 1000 microliters, because if the drop spreads, they will get intermixed, and also separation will not be good. Of course, for application, automated applicators are also available, which are going to hold the defined amount of the analyte at a time, analyte sample mixture at a time, and very precise quantity of the sample can be released onto the TLC plates. So in the photographs, you are seeing all the three types, where capillary, glass capillary, which can be manually operated. You have applicator with a defined amount of analyte sample that is picked up and applied. And further, this applicator is operated automatically. So these three different systems for sample application are there. So sample application is not really very tricky, but little care is to be taken when you are handling it. When the sample is applied to the plate, it is to be applied at 2 to 2.5 centimeters from the edge. Of course, you can use micropipette or microsyringe or the automated samplers that are used, but you have to see to it that you are not going to apply the sample very close to the edge. You are going to leave some space from one edge, and then you are going to apply the sample. That is very important. The transparent templates to facilitate the correct location of the sample are available commercially. That also can be used. The solvent may be removed from the spot. That is very necessary, because many a time the solvent system used to solubilize the analyte, and that is the solvent system that is present in the mobile phase, are different. And if the two may get mixed, then there is going to be a interference in in the efficacy is going to get affected, and interference in the running of the system. So it is very necessary that after the spots are applied onto the TLC plate, the spot must be dried. So for drying, it can be done by gentle heating, or you can use the hot air blower. Care must be taken that if the sample analytes are volatile, then you have to allow the evaporation of the solvent without application of heat. So you are going to apply more sample once the first drop dries, because what we need is adequate amount of the sample. It should not be overloaded. At the same time, it should not be less that the separation cannot be visualized. So sample application is uh, the step that needs a bit of practice, and that can be achieved with multiple trials, because loading of appropriate amount of a sample mixture using a capillary by manual mode is a tricky press. Now, when we go to the next slide, that is to talk about the material that we have used for preparation of uh, the stationary phase. So, spontaneous polymerization, dehydration of aqueous silicic acid, that also can be used. Of course, when we talk about silica gel, which is the most popularly used stationary phase for TLC as well as for HPTLC plates, important is the porosity, because the silica gel characteristics are going to decide the factors like porosity. The porosity of the plate will decide the flow or the resistance, the particles which are going to move. The particle size of the silica gel also is going to be important, because it is going to ultimately decide the polymerization efficiency and the pore size of the gel casted or the layer casted. That ultimately will decide the development time. So, the characteristics of silica gel particle size is very important. The silanol groups which are present on the silica, they are generally uh, approximately 8 per micromole per meter square area. So, this is one factor to be taken into consideration. And second is the pore diameter. So, 40, 60, 80, 100 Armstrong pore diameter silica are available. Most commonly uses 60 Armstrong pore diameter. And the specific pore volumes, they range between zero point 0.5 to 2 ml. So, when we are just preparing a TLC silica plate, all these factors are to be taken into consideration, which include the pore size, pore diameter. So 60 Armstrong diameter silica gel is commonly preferred. Then the specific surface area, which is uh, going to range from 200 to 800 square meter per GR. Similarly, the specific volume these pores are going to hold. So specific pore volume in the range of zero point 0.5 to 2 ml is generally used. So classical silica for TLC plates have a layer thickness of, as I said earlier, uh, depending upon partitioning or preparative analysis, zero point 0.2 to 2 millimeters. Mean particle size is about 10 to 12 micron. In the silica gel using thin layer chromatography, separation occurs by wedge groups which are attached to silicon atoms. So interaction between these groups and the analyte, as well as the hydrogen bonding and the dipole interactions with the surface cyanolar groups and lipophilic mobility of the lipophilicity of the mobile phase. So when a analyte is going to move onto the TLC plate, the factors which decide the process or the efficiency of the process are the silica gel pore size, the diameter of the particle, the volume it holds, the thickness of the layer that is prepared, and further the number of OH groups which are present as a SiOH groups on the silicon atom, Si and hydroxyl groups attached to it are going to decide the efficiency of the process. So these hydroxyl groups are going to have interaction with the analyte molecules, their functional groups. So it can be through hydrogen bonding, it can be through dipole interactions, and also the lipophilic nature of the mobile phase that is chosen. So different types of these interactions are going to decide the rate of movement of the analyte along with the mobile phase and that retention on the stationary phase. So as we know, the analytes can be of two types depending upon the polarity. So the polarity of the analyte is going to decide how strongly it is going to interact with the stationary phase or how strongly it is going to interact with the mobile phase. Generally, silica gel is recommended for separation of polar molecules. Say example of like lipids, glycosides, peptides, steroids, surfactants, or vitamins also can be separated. Fatty acids can be separated. Bile acid components can be separated. Aflatoxins can be separated by TLC, so on and so forth. Now next comes the mobile phase, which is the solvent mixture that we are going to use. And it is very important to talk about the mobile phase. Here, it is going to be a mixture of solvents. It cannot be always one solvent that is used because one solvent is going to limit the performance of the system as the interaction of this solvent system with the analyte and a group of analytes. So, separation of one of the analytes may occur, but separation of all the analytes using one single solvent may not be attempted. So, generally, mixture of 5 to 6 components that is generally used. Of course, it is not necessary to have 5 or 6 specific number, but you have to look for the polarity of the analyte and the solvent that you are choosing, and a mixture of these solvents you have to prepare. So, how many components are there? It doesn't matter, but we have to prepare a homogeneous system. And how the homogeneous system would look like, that is, after you mix all the solvents and prepare the solvent system, it should be clean, clear, and there should not be any sign of cloudiness. Now comes how to choose this solvent system. So, very importantly, it is required to determine the solubility of the sample in the solvent system. So, the desired mobile phase should be the one which is going to give you highest possible solubility. You have to balance out the sample affinity for the solvent and for the stationary phase to achieve the separation. That is the basic criteria. But at the same time, good solubility of the analyte in the mobile phase is also required. Now, generally, if you take the example of paper chromatography, the stationary phase is water because it is the water molecule that is adsorbed to cellulose. Similarly, in case of SiOH, you are going to have these hydroxyl groups, and the mobile phase, which is less polar, flows over the polar stationary phase. The mobile phase may not be necessarily immiscible with water if water is used as one of the components in the solvent system. So your solvent system may be a composition having water as one of the components also. The stationary phase water is that is of cellulose, or in case of silica gel, it is tightly held on the matrix. That is cellulose in case of paper and silica atoms of silica gel. So it is not going to mix up with the mobile phase, right? So the mobile phase can have water as its one of the components of the solvent system. And of course, other various solvents like alcohols, acids, or maybe ketones, esters, amines, phenols, or even hydrocarbons. They are used in specific proportions, and the suitable solvent system is prepared that would give us the better resolution of the sample components. The resolution should be satisfactory. So, selection of the mobile system should be such that you have to take into consideration the polarity of the analyte and the polarity of your mobile phase, and then how well it is going to be solubilized in it and how strongly it is going to interact with the mobile phase. At the same time, partitioning has to occur. The analytes have to get separated. So, selection of a solvent system is the step that requires research. Of course, there are other factors apart from optimum separation that are to be also considered before we go for choice of a solvent system. One important consideration is to limit the number of components in the solvent system. As I said, generally up to 5 6 solvents are mixed, but you have to choose the appropriate solvents while preparing the mobile phase. If there are more components in a solvent system, more difficult it will be to maintain a saturated atmosphere in the uh, chromatography chamber. Now, once you have loaded the plate, you have prepared the solvent system, you have poured the solvent system in the chromatography chamber, and then you are going to load your chromatography plate, or you are going to place this plate into the TLC chamber, and then it is locked. But one has to remember that before we are going to load the TLC plate into the chamber, you have to keep your TLC chamber ready with the solvent system in it. So TLC chamber is the glass plate with its tight fitting lid in which you are going to pour the mobile phase and allow it to sit for some time. So the solvent system which is prepared will equilibrate the interior of the glass chamber. That is, the vapors of the solvent system will saturate the glass chamber, which is very essential. So, if number of components in a solvent system are many, then complete and good saturation of the chamber will be difficult. It is very required to maintain the saturated atmosphere in the same chamber. But if we choose a solvent system with many components and they are going to have different evaporation rates and they may not match. So different extent of evaporation of the solvent components can change the composition of the solvent and can lead to uh, anomalies of separation. That is, not proper separation would occur. So solvent system selection is a important step. Also, the temperature is another factor that is to be taken into consideration when you are operating the TLC. In the development step, you have to decide the right temperature because the evaporation of the solvents is the effect of the temperature. So you have to choose the temperature for the development and it should be decided after careful observation about each solvent and its evaporation temperatures. So the temperature must be maintained within strict limits during the entire experiment. So overall, when we talk about the mobile phase, the characteristics of the solvent should be summarized as the one which should give a good partitioning, a good separation. So partition coefficient of the substances to be analyzed should range between 1 to 100 when you are choosing the solvent system. The solvent should be removable from the TLC plate or the paper if it is paper chromatography without taking it to very high temperature. So the solvent system should be stable also. Stable not with reference to temperature alone, that is evaporation of the particular solvent at a given temperature at a faster rate or low rate. However, it should not get oxidized when you are going to allow it to run over or when it is prepared. So the stability in terms of chemical stability is also expected. Some solvents, for example, say phenolic solvents, in ammoniacal environment, they react with small quantities of copper if it is present in the paper and they get oxidized and they produce the black or brown spots on the paper. So similarly in TLC, you have to take care that the solvent system doesn't go into its oxidized form and is not going to have uh, erroneous spots getting developed at the end of TLC. So, going to the next part of the TLC, to summarize the mobile phase solvent system, the solvent consists of um, a mixture of solvents that you have to choose, which will be stable, which is going to have a good partitioning effect. A good partition coefficient would be generated. It will be working at in uh, tune with the stationary phase, as partitioning between stationary and mobile phase is a very crucial step, and preparation of a mobile phase with minimum number of components with better separation or good separation is expected. The TLC when we talk about, we have to take into account a few important points. As I said earlier, the mobile phase components, the solvents are going to be getting into their vapor phases, especially if we are having organic solvents in the solvent system like methanol, ethanol, or even chloroform, which are going to be evaporated at room temperature in the regions like Pune, that is 37 to temperature, 38 degrees temperature. Uh, the evaporation of organic solvents is taking at a higher rate. Of course, each solvent has its own evaporation temperature, But at room temperature, when we are conducting the experiment, these are going to go into the vapor phase, and these vapors have to saturate the chamber. Saturated chamber is going to give you good separation, because this gaseous phase is the one which is going to be in equilibrium with the entire system. If there is presence of air or moisture, then this gas phase can influence the results of separation. And this influence is going to lead to significant variations in the results. So it is very important to choose a right solvent system, fill it in the chromatography chamber, log the chromatography chamber properly so that the vapor phase is saturating the chamber properly and uniformly. Now, next comes the part of the stationary layer that is already weighted with the mobile phase, is also going to contribute to the formation of the equilibrium. So, during development, molecules are continuously going to move to and fro or back and forth between the free and adsorbed states. And a balance of intramolecular forces is going to determine the position of equilibrium and thus the ability of the solvent to move the solute up in the plate. So, selecting a right solver system, preparing a saturated chamber are the key steps when we talk about the mobile phase of TLC chromatography. Now, just as a matter of uh, curiosity, you can attempt to check your to boost your curiosity or to check your awareness. You can try out solving this question. I have given a few uh, solvents. You have to arrange them based on their polarity. So it includes water, silica, ethanol, methanol, cellulose, paper, hydrocarbon coated silica, only silica, and so on. So if you know the basic property of these solvents, their polarities, so basics of chemistry we need to revise if we want to go for separation or analysis of biomolecules using TLC or even any chromatography. So please read about polarity, hydrophobicity, hydrophilicity, the functional groups of different solvents and substances, so that it will be easier for you to work in the laboratory and choose the right chemicals for the selected process. Now, let's go into the types of um, TLCs that we are going to run and the amount of sample to be applied, how long we are going to keep, how to visualize these. So it's kind of a summary sheet I'm trying to present before you, wherein we will talk about the different types of TLC, that is qualitative type, quantitative type, and preparative type. So though the basics, as I said, like the type of stationary phase that you need to select, the thickness of the stationary phase you need to select, depending on the purpose. The purpose could be qualitative analysis, quantitative analysis, or preparative. So depending on that, there are variations with respect to the thickness of the stationary phase, the material used for preparation of stationary phase. Similarly, it varies with reference to sample volume. So it is very less in case of qualitative, but when it is to preparative, it is to be up to 1 ml as against qualitative where it is as less as 2 microliters. The sample amount, of course, as I said in TLC, is giving us good results even in microgram quantities. But if it is for preparative purpose, the quantity should be up to in the range of 5 to 500 milligrams. Then only you will be able to harvest the analyte, because you want to have a pure, purify the analyte from the mixture. Sample application, then layer thickness, development distance, development time, and visualization methods, they also are going to vary depending on the type of the TLC, whether it is qualitative, quantitative, or reparative. So in general, there is going to be a competition between the mobile phase and the stationary phase for the analyte. The analyte will keep interacting with the functional groups on the mobile phase and that on the stationary phase, and depending upon the strength of interaction, if it is strong interaction, it will be held in that particular environment. So accordingly, you are going to have adsorption and desorption of the analyte on the under the stationary phase and within the mobile phase. And analyte is going to move faster if it is going to be interacting more with the mobile phase. Now, when we talk about plate development, separation most commonly takes place in glass tank that contains the developing solvent, and generally the volume of the solvent also is very important because uh, 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 the TLC plate that you are going to immerse along with its analyte loaded onto it, the analyte mixture should not get dipped into the mobile phase. It should remain above the level of the mobile phase. So the mobile phase level in the chamber also is very important, and generally 1.5 centimeter depth of mobile phase is used. It is allowed to stand for about at least 1 hour with the lid over the top, over the top of the tank, and to allow the saturation, right? As we talked about. So equilibration of the chamber is another important step. After equilibration, the lid is removed. The thin plate, the thin layer plate is placed vertically in the tank so that it stands in the solvent, and the lid is replaced. Separation of the compounds then occurs as the solvent travels up to the plate. It is also possible to develop the plate in a horizontal plane. Here in the discussion today, we are talking about only, I mean, we have seen the photographs only of the vertical system, but in the horizontal plane also, the TLC system can be run by connecting the sample end of it to a reservoir of mobile phase by means of the wicks, suitable conducting wicks. Of course, it is preferable to keep the system at a constant temperature, as I told you. So there is no anomalous separation due to differential running of the components in the solvent system, because with the change in temperature, the mobility of the solvent components also is going to get changed. So it is better to maintain a uniform temperature. And when we are running TLC plate, the important thing is that, or the biggest advantage of TLC is that the speed. So you are going to have the separation achieved in about say 30 minutes. And in certain cases, if the molecules are of high molecular size, then it may be up to 90 minutes. But so by 1.5 hour time, you can get the separation achieved. Of course, to improve the resolution of partitioning or adsorption methods, we can choose the advancement that is two-dimensional chromatography. But before we go to that, let's go to the next step uh, in the TLC system. That is, we are going for one directional TLC. Once that one directional TLC is done and separation is not adequate, TLC can be run in the second dimension also to have a better separation. But what does separation means? How it looks? How to see that? Because if you are separating ink samples by TLC, you can surely have colored spots. But if it is carbohydrate mixture, they are colorless and you cannot see them. So visualization is an important step when it is TLC. So organic compounds most commonly appear colorless when we talk about the TLC, and on the white background of the TLC plate, you cannot really visualize the separated analytes. So to visualize these, you have to convert them into some visualizable entities, right? So of course, to convert them into some another thing by addition of chromophore group to it, or by treatment with certain selective reagents, maybe a destructive method or maybe non-destructive method. In a sense, destructive method is a one where the compound is going to get converted into entirely a new different molecule, so it cannot be further used. Its original nature is changed, so purity is not there, and it cannot be further used. As against that, if it is non-destructive method, you can retain the originality of the molecule, the purity of the molecule, and it can be further utilized in further experiments. So, in case of non-destructive methods, the very common one is visualizing the plate under UV light, which is non-destructive. But if you are using a chemical reagent like a charring reagent, which includes sulfuric acid and other agents, so in that case, the molecule is going to get charred, and it cannot be further used. So it's a destructive method. So here I'm trying to show you some photographs wherein uh, different modes for visualization are attempted. The first slide is showing UE as a method to visualize the spot. So when you hold your dried TLC plate after it is run, after the development is done, and you hold it under UV, it will give the specific fluorescence. You will get colored spots. They can be observed. And in case of analytes like the toxic molecules from fungi, right? They may give you fluorescence. Certain aromatic molecules, they may give, if they have their inherent fluorescence under UV, it can be very well easily seen. In the second case, it is iodine that is used. So iodine crystals, they go into vapor phase very easily. So by the time your TLC plate is developing, you have to prepare another glass chamber in which you are going to put iodine crystals and cover it tightly. So iodine at room temperature is going to go into vapor phase, and the vapors will saturate that glass chamber. So once TLC run is over, take the plate out, dry it, and put it into iodine chamber. Iodine will react with the biomolecules and will give the colored spots, mostly the brown spots, of course. And as you see in the second plate, the brown spots which have developed due to complexation of iodine with the analytes like, say, amino acids or carbohydrates, etc. Then you can have specific reagents like ninhydrine for amino acid that can be used selectively, or you can have vanillin that can be used for some of the analytes like alcohols to give color complexes. So development of visible spot is very important, and that is referred to as analyte detection. So several detection methods are available. Examination of the plate under UV light will show the position of ultraviolet absorbance or the fluorescent compound present in it. So many commercially available thin layer absorbents, they are there, which contain the fluorescent dye also. When you are um, observing the plate under UV light, the separated components will show up various colors as blue, green, or black areas on the fluorescent background. So not necessarily the sample analyte his own fluorescence, but the plate fluoresces, and against the plate, dark colored spots can be very well detected. So UV is the first method. In the second, we talked about the iodine vapor, which is again more commonly useful for or efficient for unsaturated compounds to be investigated. So that is second method. Third is spraying the plate with a specific color agent, as I said, for example, ninhydrin to locate the amino acids and peptides. Of course, if the compounds in the sample are radio labeled, then this plate can be taken for autoradiography also, where it will detect the spots as dark areas on the X-ray film, or maybe in advanced cases you can have a radio chromatograph scanner also. So it will scan the plate and give you the pics, and the chromatogram will be presented. Uh, Also, as I said earlier, the charring agent, which is a non-specific one and can be applied to variety of biomolecules, which includes sulfuric acid uh, and ethanol, and this mixture is sprayed onto the plate, and the plates are heated up at say around 110 degrees Celsius, and the compounds will get charred, that is burned, due to sulfuric acid interacting with it, and brown color spots will develop. But of course, it needs a lot of care while handling sulfuric acid, and that too at high temperatures. So these are the different methods which are used to detect or visualize the analytes. Now, another important thing to be talked about is the movement of compounds on TLC may be characterized just not observation. It is, I'm talking about characterization, and that is with the help of RF value. Just in the previous slides, we talked about retention factor, the RF value, which is a measurement. Of course, as I said earlier, it is going to change for one analyte, it is going to change depending upon the solvent system chosen. So you have to optimize the solvent system and compare the RF value of a given analyte in a given solvent system and the known standard RF values for that analyte for the given solvent system. And then you can compare about the presence or absence. So whatever RF value you are having for sample 1 in a given solvent system, you have to choose the solvent system which is same as that you have used. Look for the RF value that matches with your sample analyte, and that could be an indication that probably the sample is same as that what is referred in the standard. But sometimes it may not be truly reproducible. But as an initial measure, you can use RF. Another thing that you can use this data to find out is the amount of the analyte at a given spot. So the amount of the compound which is present in a given spot can be determined in different ways. So maybe on plate quantification that we have to do, where radio chromatograph scanning is done out of different development methods. If we are using radio label compounds are there, and radio scanning if we are using, it will be very easy. So densitometry will give you the amount of light produced or light absorbed, or in case of radio scanning, the amount of radiations emitted. So all these things can be possible with the help of densitometers which are commercially available, and they can measure the ultraviolet lights or visible absorption of the compounds, as well as simultaneously they will give a complete absorption spectrum for the compound for identification purpose. And when it comes to off-plate quantification, it may be carried out where you are going to scrap off the spot, and without um, I mean without mixing it with the surrounding stationary phase, you have to just pick up that spot and elute it out in a suitable solvent system and perform the analytical test to identify the analyte. Of course, many a times spectrophotometer like devices are attached to TLC systems, which can give you analysis of the analysis to a greater extent, and characterization of the analyte also can be achieved. So with this, the second video we have uh, studied TLC. The second video to study TLC. There is one more which will talk about some uh, variations and advancements in the TLC technique.